Hello everyone, welcome to this online course on manufacturing processes. I am Kishore, Assistant Professor in the Department of Mechanical Engineering, MLR Institute of Technology, Hyderabad. So today we'll discuss about aspiration effect. We'll see what is the meaning of aspiration effect in casting. Then we'll see through mathematical calculation that what does this aspiration effect means. That's why this derivation has been written. Derivation means simply we'll see what actually happens during aspiration effect. Then whatever the result we'll get during that stage, that result we'll discuss in detail. So in the third part we'll also see how this aspiration effect can be avoided, and finally we'll take one numerical from the previous gate question, so that whatever concept that we have studied will be more clear. So we'll start with the aspiration effect. First of all, we'll see what is the meaning of this aspiration effect. As we know, in the casting there is a gating system. Already we have studied about this one. So through that gating system we pour the molten metal. That molten metal finally, through many part of the casting, it finally reaches to the cavity where it will solidify, and finally after solidification we take out the cast product. So during moving from pouring basin to the mold cavity where it finally solidify, many stages comes over there. So what actually happened in between? Suppose metal we are pouring in the pouring basin. Suppose this is the pouring basin and this is the sprue. This is runner and then this is the mold cavity. Finally it is reaching. So suppose this molten metal is passing through all this area, and whenever the pressure value, all the parameters will be there. At what velocity this metal is moving, what is the pressure at each and every point. Suppose at this point what is the pressure, at this point what is the pressure, at this point what is the pressure. Similarly, what is the velocity in the sprue, what is the velocity in the pouring basin, what is the velocity in the runner. So all these parameters actually affect what the final cast that we are going to get. So mechanical property, many properties will be dependent upon that one. One of the property or one of the effect is actually this aspiration effect, which is actually based on the parameter. So suppose we are pouring metal inside this one, and if at any stage of this gating system, if the pressure value is less than the pressure of the atmospheric pressure, outer part, we know all these pressures are atmospheric. So if pressure at any point starting from here to here, if at any point pressure is less than the atmospheric pressure, then what will happen? Whatever the air particles are at the outer part, means their air particle, this will rush inside the mold cavity. This will rush inside this gating system, and what will happen? This air will go and it will finally mix with this molten metal, which is actually finally reaching to the mold cavity. So once it will mixed over there, that will be entrapped over there with the molten metal, and once it will be entrapped over there, finally it will appear as a form of defect, which is known as cast defect. So this is actually known as aspiration effect. So that actually has been written here: unintended entry of air or gases in the molten metal due to improper gating system design. Gating system has not been properly designed, then also it may come, or the another is negative pressure condition. That's what just now we discussed. So if pressure at any point of this is less than the atmospheric pressure, obviously air will rush and it will go inside, and those air will be mixed with the molten metal, and that molten metal will be in the form of entrapped gases over there, and those entrapped gases will finally appear in the form of cast defect. So this is actually known as aspiration effect. So obviously if you want a casting which is defect free, so obviously we'll have to avoid this aspiration effect. So what actually happens because of this? So these two prominent defects are there if aspiration effect is there. That porosity is nothing but the entrapment of the gases, and here we can see it is nothing but the entrapment. So what will happen? Once air will be entrapped over there, it will appear in the form of defect, which is known as porosity. And the second one is that oxide inclusions. So this air particle which is going actually inside the mold cavity and mixing with the molten metal, those we know the air particles are there. In that, oxygen is also there. If oxygen is there, and suppose the molten metal that we are pouring, it will mix with that and it will form metal oxide. So that's what has been written here. Oxygen reacts with the molten metal and it forms non-metallic inclusions which also appear in the form of defect. So aspiration effect is actually nothing but the unintended entry of air or gases in the mold cavity. Now through mathematical analysis we will see what is the meaning of these negative pressure conditions. So in next we will see in analysis. First I am drawing the diagram so things will be more clear from there. Suppose this is the pouring basin and this is the sprue. This sprue is having uniform cross section, means from starting to last. So suppose this is the pouring basin and it is having some, we in three parts we are dividing. This is having some height. Suppose we are taking this one as h1 and this is the one point. Suppose we are taking this point as 1 as a reference, this point we are taking 3, and suppose this point we are taking at 2. So this sprue is having total height from top to bottom is h2. Okay, so if this is the pouring basin, and finally this molten metal of course will reach in the mold cavity. Suppose it finally reaching in the mold cavity. Suppose this is the mold cavity. Okay, so this molten metal is going inside. It is going inside. Why we are drawing this? We are going simply to see what is the meaning of negative pressure over there. So suppose molten metal, it's pouring over there in this sprue and finally it is reaching to the mold cavity. Okay, so we are assuming this is open to the atmosphere. This point of course is open to the atmosphere. So suppose the pressure at this point is P1 and this is also open to the atmosphere and pressure at this point is P2 and we are taking atmospheric pressure at the reference. So obviously this P1 will be equal to P atmospheric and this will be 0. This also will be equal to P atmospheric and this will be 0. Okay, so if we apply Bernoulli's theorem between these two, and as these 2 points are having equal cross sectional area, so if we'll apply continuity equation between point 2 and 3, so if we'll apply continuity equation between 2 and 3, so we can write area into velocity, that is A2 V2 is equal to A3 V3. So we can write, we are taking this point and this point. So as these two have equal cross sectional area, so A2 is equal to A3, so it will be cancelled out. So from here we can write V2 is equal to V3. Okay, so suppose next we are applying Bernoulli's equation between point 1 and 2. If we are applying Bernoulli's equation, between point 2 and 3. If we are applying Bernoulli's equation between point 2 and 3, so we can write pressure at point 2, that is P2 upon rho g plus V2 square upon twice g, plus we are writing this Z2 height or this potential energy. This is equal to P3 pressure at point 3, P3 upon rho g square of the velocity upon twice g plus Z3. So already we have seen this P2 is open to the atmosphere, so this pressure is 0, so this whole term will be cancelled out. Okay, and this V2 and V3 are equal. Just now we have proved this one, because area of cross section at this and area of cross section at this, these 2 points are same. Here area of cross section and here area of cross section, here area of cross section and at this point area of cross section are same. So we have already seen this V2 is equal to V3, so these two terms will be cancelled out. So finally what we are left with, we are left with Z2 minus Z3. This is equal to this P3 pressure at point 3 upon rho g. So if we'll see this Z2 minus Z3, this one we are talking about, this point is actually 2 and this point is 3. So Z2 minus Z3, this is actually negative. This value is negative. This value negative means that these two are density and acceleration due to gravity. These are the positive value. So obviously from here we can see that, or we can say that P3 is negative. P3 is negative. And P3 is negative means, what does it mean? We have already assumed atmospheric pressure at the reference. So P3 negative here is nothing but vacuum. So it is a vacuum. Vacuum means, what does it mean? Means pressure at this point 3 is less than the pressure of the atmosphere. So what will happen if pressure at this point is less as compared to the outer part? This outer part means this cavity is there and pressure. So what will happen if pressure at this sprue is less than the pressure at this atmospheric? So air from the outer part, it will rush and go inside. So what will happen once air will pass? Now the question is, sprue is made up of sand, and sand, you know, if it is made up of sand, say small pores will be there. That is, it is a porous structure. So through that pore, air will pass and it will go inside the cavity or the sprue, and it will mix with the molten metal. Once it will mix with the molten metal, it will be in the form of entrapped over there, and finally it will appear in the form of a cast defect. So I hope it is clear to everyone that what is the meaning of negative pressure and why actually aspiration effect actually happened. So now the question is, how can we avoid this one? So the simple and easy fundamental thing is, what we have to do, we have to maintain the pressure from a starting point to end point, so that at any stage while pouring the molten metal, pressure shouldn't be less than the atmospheric pressure. If pressure is not less than the atmospheric pressure, then obviously there will be no rushing of the gas, or there will be no gases or the air. It will not go inside the mold cavity, or it will not go inside the gating system at any stage or at any point of the gating system. It will, if it will not go over there, obviously there will be no entrapment of the gas. So what is the basic thing that we need to do to avoid the aspiration effect? That basic thing is, we need to, while manufacturing or while preparing this gating system, whenever we are doing that, we'll have to keep in mind that at any point of the gating system, we'll have to make sure that the pressure value should be always either more than, or in worst case it should be less, equal to the atmospheric pressure. It shouldn't be less than the atmospheric pressure. So if air pressure will not be less than the atmospheric pressure, then what will happen? There will be no aspiration effect, and if there will be no aspiration effect, obviously there will be no entrapment of the gas in the casting. So obviously the cast product produced will be defect from the aspiration effect. So to make this concept more, to emphasize this concept or make it more clear, we have taken one numerical also. So we'll take this numerical, we'll try to solve. This is actually gate problem. It was a previous gate problem, the standard problem. Gate 2007, this problem was asked. I have taken from the starting itself. When we started this course, what we are doing, we are taking only standard problem. Whatever concept we are learning, to emphasize those concepts, we are taking standard numericals generally from the gate. So today also, to emphasize or to make it more clear, this aspiration effect, what we learned today as a concept, we have taken this numerical previous year gate question. So what this numerical reads, a 200 mm long down sprue has an area of 650 mm square. 650 mm square, where the pouring basin meets the down sprue. Okay, so this information has been given. That is at the beginning of the down sprue. So if we will draw the diagram, things will be more clear. So I am drawing here the diagram. Suppose this is the diagram. So here the sprue is, and this is the pouring basin. Here somewhere mold cavity is there, where it will finally reach. So here this area has been given. This area actually is given. Suppose we are taking this point as 3, and as we are considering in the discussion also, we considered this point. So we are taking this at point 2, this point as 2, and this point as 1. This height we are taking h1, and this up to this one, this height, I mean sprue length, we are taking as h2. So here area is given. Which area is given? A3 is given. So this A3 is given. What is that is given? This is A3 is given 650 mm square. This value is given. Now this height is also given. This sprue length is given, and what is this? This is 200 mm. Okay, what is next? A constant head of molten metal is maintained by the pouring basin. This one we are assuming this is having a larger area, so that whatever the molten metal is coming inside this screw, so it has been given, it is maintaining the constant head. Constant head means its velocity with which it is coming down. If we will consider here this point 1, so actually it is 0. Okay, now that's why this point has been written. Okay, the molten metal flow rate is 6.5 into 10 to the 5 mm per second cube. So this Q is given. Q means discharge or the flow rate with which this molten metal is flowing inside, that has been given, and it is given 6.5 into 10 to the 5 mm. Sorry, this has been actually given wrong. Actually this should be mm cube per second. Okay, this should be mm cube per second. Actually it is volume per unit time, so this is mm cube per second. My mistake, it is given. Okay, considering the end of this down screw open to the atmosphere and acceleration due to gravity, the value of G in this problem is not given 9.81, it is given 10 to the 4 mm per second square. Whatever the value is given, it is very, very important. Don't assume that the G value will be 9.81. So whatever in the problem it is given, we have to consider that value only. Okay. So what we have to calculate the area of the down screw at the end. So actually we have to calculate A2. So in the problem it has been asked what will be the value of the A2. So this is the problem. So what we have to do, it's a very important thing here has been given, avoiding aspiration effect. So clearly in this problem, it has been given that avoid aspiration effect. Just now we have discussed that if we have to remove the effect of aspiration, what we have to do? We have to take care that while pouring the molten metal from the pouring basin to reaching to the mold cavity, pressure at any point in the gating system shouldn't be less than the atmospheric pressure. In worst case, we can assume that the pressure should be equal to the atmospheric, but not less than that one. So keeping that point in mind, if we are using that one, easily we can solve this numerical. So we'll see how to solve this numerical. So suppose we have seen at this point pressure was negative. So what we are assuming in this one, to solve this numerical, simply we are assuming that pressure at this point, that is P3, is equal to the atmospheric pressure. That's what the requirement is, to avoid the aspiration effect. So already this is open to the atmosphere. So its pressure at this point is 0 because we are taking atmospheric pressure as a standard. This is also open to the atmosphere. So pressure here also is equal to atmospheric pressure. So it is 0. So we can write, so simply we can write P1 is equal to P2 is equal to P3, and we can write this P atmospheric, and this is equal to 0. So in this problem, this area A3 is given, but velocity is not given, and this Q is given. So through continuity equation, we know if we can write Q is equal to A2 V2, and this will be of course equal to A3 V3. Okay. So from here we need to calculate, sorry, this is A3. So this A3 is given, but V3 is not given. So from here we can calculate V3. What will be V3? V3 will be simply Q upon A3, and this value is given. So Q is given in the problem. What is the value? 6.5 into 10 to the 4 mm cube per second divided by this area is given. What is the value? This 650 mm square. This 650 mm square. So once we will calculate this one, we'll get the value of the area, and what will be, sorry, we'll get the value of V3, that is velocity, and it will comes out 1000 mm per second. Okay. So now we got the value of V3. So now we have A3, we have V3, and this area we have to calculate. What this area? We have to calculate this. So what we will do to calculate the area here, first we will apply Bernoulli's equation. If we will apply Bernoulli's equation between these 2 points, we will be able to find out the value of velocity at this point. Once we will get the velocity at this point, So through this equation, we'll be able to find out the value of 80. So it will become very easy to calculate. So first what we are doing next step, we are applying Bernoulli's equation between point 2 and 3. So what we can write simply P2 upon rho G plus B2 square upon twice G plus Z2. This will be equal to P3 upon rho G plus V3 square upon twice G plus Z3. Okay, we can write this is 0 because it is equal to the atmospheric pressure. This is also equal to 0. Why? Because this is also, we have assumed to avoid this aspiration effect. So now we are left with V2 upon twice G plus Z2. V3 just now we have calculated. So we just have to put the value over there. So what we will do, once we will put this value, so we can write here V2 square upon twice G is equal to, we can write this V3 just now we have calculated. So let me put the value. So V3 just now we have calculated, it is 1000. So a square of this one upon 2 into G value is given in the problem. What is 10 to the 4? So 10 to the 4 plus this Z3, and now we are taking this Z2 in right side. So Z3 minus Z2. So this Z3 minus Z2 is also given. It's nothing but this sprue length. So this is also given in the problem. So this is 1000 square into 2 into 10 to the 4 plus this will be 200. So if we'll solve this one, so from here we'll get the value of V2, and so what we'll get this V2 from, while solving this one, we'll get the value of V2 2236 mm per second. So this is the velocity at this point. Now we have to calculate area. So we know from continuity equation we can write Q is equal to A2 V2, means area at point 2 into velocity of the molten fluid or molten metal at point 2. So from here we can write A2 is equal to Q upon V2. This Q is given in the problem. What is the value of this Q? This is 6.5. So this is 6.5 into 10 to the 4 upon V2 just now we have calculated 2236. We will calculate this one. So finally we will get the value 290.7 mm square. So this is the answer. Okay, sorry, it is coming behind. So let me write here this answer. I am writing here. So finally while calculating we have got the value 290.7 mm square. So this is the final answer. So through this we understood what is the meaning of aspiration, what is the meaning of aspiration effect in casting, what is the meaning of negative pressure, why actually it is happening, and because of that what kind of problem will be there in the casting. And also we saw that how we can avoid this one, and to make it more clear we have taken this numerical and we solved to just emphasize whatever the concept we have learned. I hope it was enjoyable and it was fruitful for you. We'll again meet you in the next video. Thank you.